All right, same thing. All the questions with the nuclear symbol, all right. Okay. If there's anything you want else want me go through, you just let me know. I'll go through. What questions are just type in the chat or I'm yourself, lor. Yeah. We start now. Okay. So this is EM and EMI. Of course, EM and EMI will cross into AC quite a bit as well. So you'll see quite a bit of AC questions here, lah. So it's a very natural overlap between EMI and AC, right? Okay. Let's look at the first one. This one is I think the MCQs are quite straightforward lah, so we should be able to do them quite quickly. 4 questions only. Right. So here you have a coil, you have a wire loop. Okay, so the wire loop, the current is going in this direction. So going up like that and down back here. Right. So it's a current of I inside it. Okay, so length X and Y, current I, B field of B. Right. So we know that if we want to find our magnetic force, EM force, right? We go for F equals to BIL sine theta. Okay, so this is the part that determines you need to have the angle there, right? Okay, so we need hence if you want to have maximum force, right? So remember when theta equals to 90, your sine theta is equals to 1, right? Then when 0, then it's 0 lah. So that means you will only have magnetic force for the highlighted portions. This one and this one, right? The red ones here, right? They do not have any force on them because the red portions, right? The current is flowing the direction of your flux density. Okay, so this direction is the same as your flux. So the angle between these two is 0. Okay, so you only have force for these two portions. So here, right, the force, let's say you write the force on SR, right? It's just equals to B I Y. Okay, of course we can write the sine 90 back, but because we say that, so we know that sine 90 is equals to 1, so we don't write it lah. Okay, then same for FTU. FTU, right, is equals to BIY as well. Alright, equal in. Right? So that's the rules are the first statement, because first statement A, right, force on side SD. Side SD, there's no force, so this is wrong. Okay, then net force perpendicular to the magnetic field. Okay, so let's check this one first. Just see. Okay, see, right? If we look at on ST side, right? SR side. SR side using a left hand rule, right? The force is towards the is going into the wall. Okay, and then on the other side, it should be coming out from the wall. Okay, so your net force is perpendicular to magnetic field. No, because these two forces will cancel each other out, because they have for these two portions here, right? Your current is the same, so your your EM force is the same as well. Okay, so this is out, and then no force acting wire loop is also out as well. All right. So the answer has to be B lah. Okay, so what is it B? We take this point here. If we take the center as the pivot, let me draw a line for the pivot here. If I take the center line here as my pivot, right? Okay, this distance here is x over 2. Okay, and same for the other side, x over 2 as well. Okay, so if I want to find the torque due to the total torque, right, is the torque due to FSR plus the torque due to FTU. All right? So this one is BIY times x over 2 plus BIY times x over 2. So total is just BIYX. Okay, so answer is B lah. Alright. If you have issue, just type or raise your hand whatsoever lah. Okay, this one here, okay, this was an easy question lah, but I think sometimes there's a confusion in the formula for flux linkage. Okay, so we have uniform B field of flux density 0.50 Tesla. Sorry, 0.50 Tesla. Coil of 20 cm square. Coil is 15 turns at tilted angle of 30 degrees. Right. So let's recall the formula. The formula here is phi is equals to NBA cosine theta. Okay, this theta here is the angle between normal or plane, normal or coil, and B field. Okay, very important. So over here, right, the normal of the coil, if you draw it, right, it's like that. Yeah, it's red color. Over here, this is the normal of the coil, right? So this is the normal. Okay, so this is the angle that we are after. Okay, this angle here happens to be 30 degrees. Okay. Another way of looking at this is that, okay, if you were to look at the current coil, this direction, right? We can break it down into this. Okay. So let's say this is the area. This is area Y. This is area X. Okay. Hold on. Okay. So if I look at Y and X, right? Uh, X is parallel to the BB field. Okay. So if you take the normal of X here, right? This is the normal, right? This normal together with the B field is at right angle. So if you right angle, right, your cosine theta becomes zero lah. So we only want this one here. This one here, this angle, this not normal to the field, right? Normal to the coil, right, is parallel to your BB field. Okay, so this is what we want lah. Right, so we can sub in the values here lah. Okay, so okay. So when the thing about the reason why this question is actually useful is that you need to be very careful about how you apply this formula here lah. Very, very important. Okay, make sure your theta is actually the correct theta that you want. Okay, so then we sub in the formula. So this is phi equals to NBA cosine theta. So N is number of turns 15, B is 0.50, A is 20 over 100 square, and then cosine is cosine 30. Okay, so should be able to get answer from here. Issues? First two so far? Okay, moving on. Okay, so we have 23. This is an EM question. This is a charge question. Moving charge through a field. Okay, so we have do we have issue here? Okay, we have charged particles. They never say positive or negative. Not important. Okay, because we can see how it goes in there. They have a slit V passes through a slit S1, so it enters into this space here. It goes into this space, then comes out undeflected. They tell the direction of E field is downwards, right? And then, but then because there is magnetic force, so let's just assume that, let's just try for a positive charge. Okay, let's just put a positive charge here. So this positive charge over here, let's try positive charge like that, right? Positive charge have a velocity of v. Okay, then we can draw in the two forces lah. Okay, so positive charge will move the direction of the E field, right? So my electric force is actually downwards. Fe on the positive charge. Okay, so for this guy to stay to not be deflected, right, there has to be a magnetic force in the upward direction that's equals to the electric force. Okay, again, I label this as plus. All right, then if I have an electron, if this is an electron here, same thing, moving velocity of v, right? Electron goes, the electric force electron is in the opposite direction of the E field, right? So in this case, my electric force has to be upwards. Okay, and therefore my magnetic force, my EM force must be downwards. Okay, so I can, okay, then you see right now your electric forces, sorry, your EM forces are in opposite direction. Okay, this guy and this guy. Okay, but it's still okay because remember the formula for EM force for moving charge is F equals to BQV sine theta. Okay, this V is for direction of positive charge. Okay, and then if it's electron, if it's negative charge, we assume the opposite direction. So in this case, let's say for our positive charge, right, Positive charge moving to the right hand side, we just treat my V to the right hand side. Negative charge going to the right hand side, we treat the V as towards the left. Okay, so it's to balance out. Okay, so let's just work out the direction of the magnetic field first. So if we take the positive charge one right here, right? We use our left hand rule. Our middle finger is pointing to the left, to the right hand side. Our thumb is pointing upwards. So you realize that your B field has to be into the wall. Your B field is into the wall. Okay. Okay, double check using the electron now. Electron going to the right. So we use the velocity as to the left. Okay, so middle finger pointing to the left, thumb pointing downwards. The B field is also into the wall. Okay, so that's okay. All right. Then for forces, for the magnitude of the force, right? We will do because the force is equal, right? So we do Fe equals to Fe. So this is QE equals to BQV lah. Okay, supposed to find B, right? So B is just QE over BV. So E over sorry, supposed to get rid of. Yeah, so yeah, BQV. That's wrong, right? That's wrong. That's QV. Okay, so it becomes E over V. Okay, and that's 23. Okay, for 24, right? 24, we have a copper disc that is rotating in the B field, magnetic field, right? So it is rotating in this direction, right? Okay. So you have four statements here, and then you connect it. So you connect M center, connect N at the rim here, right? So here, right, what you need to do is to always consider a strip. Consider a strip here like this, like that. Okay. So let's just take a positive charge and a negative charge. So positive charges are positive charge, the current velocity is downwards. Okay, because this portion of the disc, right? The next instance, it will be somewhere here. Right. So this guy will move downwards. Okay. It's not moving on its own. You are basically forcing this whole strip of material to move, right? Okay, so the V is downwards. Then our B field is into the paper. Our B field is into the paper here. Okay. So we use our left hand rule. So again, left hand rule. Index finger pointing into the wall. Middle finger pointing downwards. You will realize that your magnetic force is in this direction. Okay, this is the direction of magnetic force. Okay. Then if I give you an electron over here, right? Electron again, this electron is being forced downwards this way, right? Okay. So if we use our left hand rule again, but now because this is the electron moving down, we will use our middle finger will point outwards. We treat it as our velocity. So our velocity field is into the wall, right? So your force is this way. Okay. So this system will cause your charge particles to redistribute themselves in this manner. Okay. You redistribute itself like this. Okay, once I have this, right? Then this guy here is a source of EMF already. If you connect this N is an M, this N is N. Okay. So basically if you connect up the rest of the circuit at this, right? This is R, right? Your current will go this direction. Because this guy is basically acting like a battery with N at the higher polarity. Okay, remember within a battery, your current goes from your positive charge goes from the lower potential up to the higher potential. So in this case, it's from M to N. Okay, this material now is acting like a battery. Okay, so current is going from steady current from N to through R to M. So it's going this way. Okay. So the question now is, let's say if I change the setup, let's say I give you the circle, I give you the same circle again, like that. Okay, like this. Okay, so this is M and this is N, right? Let's mark this point called O. Okay, if I connect my circuit this way, what current will I get? You can type if you want to answer.
There shouldn't be any current, right? Since both are positive.
Yeah. So in this case, right, on the other side, right, your positive charges will go outside here. Okay. So it will redistribute this way, lah, right? The negative charges will go inside in both cases. Oh, sorry. Yeah, I think it's a weird iPad error again. Yeah. Okay, like that. It's all going this way. Okay. So when they redistribute this way, right, you tap O and N, right? They are both at the same potential. Okay, so there's no current. There's no net. There's no potential difference. No time current. Yeah. Okay. 4A. Okay. 4A explanation part one. Okay, I'll just show you. So remember this one always, because what your magnetic force, right? Your EM force is always perpendicular to your direction of velocity. So it changes the direction of your velocity, but not the speed. So this results in circular motion. Okay, you can look at the handout over here. Okay, so it only provides the centripetal force, only changes direction and not the speed. So this will result in circular motion. Okay. Okay, then state if the charges are positive or negative. So this one again, B fuse into the plane of paper, so just label direction. Then use a left hand rule. Again, the velocity is this direction. Use left hand, middle finger pointing to the right hand side, index finger pointing into the paper. So your thumb should be pointing down. So I remove this guy. I can't tell this was. All I know is that the velocity, the force is always in this direction. Okay, so let's just take this one for consideration. This one here, right? My thumb is pointing down. My index finger is pointing into the paper. So you can see right now, my middle finger should be pointing to the left. Like that, I can feel it, right? So this this velocity here that you're using is actually to the left, like that. Okay. So if the charge is physically going in to the right? But the velocity you realize that this V here is leftwards, right? That means this has to be electron. Not electron. This has to be negative charge. Okay, because if it's positive charge, right, the velocity you use for the direction of current you use for your left hand rule, right, it should be to the right hand side. But you go to the right hand side, right, you realize that the force will end up being upwards. So it cannot be a positive charge, it has to be a negative charge. Okay. Okay. Then you're asked to calculate ratio Qx over Qy. So you are told that the radius of the semicircular path of y is double that of x. Okay. So we use that to help us. Okay, so 2 marks. Okay, so we need to talk about EM force and centripetal force. Okay, so always good to write that initial statement first. The statement about, okay, so you can say that oops, sorry. So centripetal force is provided by EM force. Okay, so from here I can write, okay, FC equals to FB. Oh no, I think typo. FB. I think the iPad is having. I think it's almost time to restart the iPad. I'm trying not to do it now. We see, and until I cannot tahan it, then I restart. Okay, so you write equation. So this is mv squared over r equals to bqb. Okay, I don't need to write the sine theta because in this case it's right angle to each other. Okay, so I'm supposed to find. Okay, I'm supposed to find compare r, right? Okay, sorry, I'm supposed to compare q. So I'm going to make q the subject. So first thing do, I strike off one of the v's first. Okay, then I rearrange this guy. I get q equals to mv over br. Okay, then realize the mass is the same. Same as different charges. Speed is the same. Okay, so this equation here, right? Everything here in the box, right, is constant. Okay, so that means Q is proportional to 1 over R. That means Qx over Qy is equals to Ry over Rx. Ry over Rx is 2. 2 is to 1. So answer is 2. Okay. And we're okay for this one, not too much. Bad. Okay. So now, okay, so we look at this one, B, there's some changes. So let's go back to the first diagram again. First diagram, they tell you that this is a vacuum. Okay, so vacuum means there are no air molecules inside. That means there are no air molecules that are acting as an obstacle, that is obstructing your charges. Okay, because remember, if you have air molecules inside, right? We talk about when we learn about alpha particles, we say that alpha particles can ionize the gas molecules around it, right? So remember, let's say we have a stream of, let's say, I'll just label them as air, as just some air molecules. Okay, so let's just say we have a lot of air molecules. AIR, a lot of air molecules here, right? Okay, let's say this way, all right? Okay, if my alpha goes through, alpha is positively charged, remember? So it has the ability to drag away electrons from here, drag away electrons from your air molecule. So when you drag away one electron from your air molecules, right, your this particular molecule or atom here becomes positively charged. That's what happens when you ionize it. So but then the act of this alpha coming through, right, to pull away electrons, right, to pull electrons from your air, right, from air molecules, right, causes it to lose Ke as well. It will slow down. Okay, so eventually comes to a stop. So we learn that alpha doesn't travel a long distance in air lah. That's the main reason. Okay, so same thing here. Going back to this question here, right? Now you have uncharged gas particles inside this space here. Okay, so here, very important. Okay, and then now you can see that now your path becomes like this. It goes in a spiral. There's an inward spiral. Okay, so question is, why does it go in an inward spiral? Okay, so explain using any relevant equations. Okay, so this one, of course, if you can explain words, you can do that, but the question already give you so much space. I think it's clear that you should make use of equations to make your life easier. Okay, so we start off with same thing using our centripetal force equation, right? So we have B Q V equals to mv squared over R. And then in this case here, right, you can see that the R is actually reducing. Okay, so at first the R1 is like that. Then the next one, by the time it comes, let's say here, it is smaller like this, and then it gets smaller and smaller. All right, so R is actually reducing. Okay, so to make R the subject, so we're going to change this guy around. So R equals to mv squared over bqv. So we have mv over bq. Okay, so we can see that this block up terms, these are constants. So basically, I can write the equation, continue, this one, that means R is proportional to V. Okay, so in order for your R to drop, right, your V has to drop. Okay, so here, then now you can start explain. So you can say as charged particles pass by air molecules, gas particles, right? They lose energy, hence speed, due to collisions or ionization. since radius of orbit is proportional to speed of charged particle. So I know that. So since therefore V drops, R will also drop. Okay. So you can don't need to read my bad handwriting. You can just look at the handout. Okay. Yep. So we have. Yeah. Okay, next we work out the time taken for one. We work out expression for time taken for the period. So in terms of M, Q, X, and B. So let's see. Okay, so we will write this. Okay, now we will use another form. We will write okay, remember always start off with your centripetal force provided by EM force. Always remember have this line. Okay, so this EM, I think it's electromagnetic because you don't get confused with EMF. Okay, this is not EMF, this is electromagnetic force. Okay, so here we can write okay, we're going to use the M R omega square form because I know this period. Period I know is I know that omega is equals to 2 pi over t, right? So I want that. Yeah, just erase it. I think let's see. Okay, so here I will write this back color. So this is M R omega square equals to BQV. Okay, I can get rid of this one first. Okay, so this BQV can be expanded to BQR omega, right? And this is MR omega square. So I can, sorry, no, I don't show you this. Okay, this R omega square, I can take out R omega. So this becomes M omega times V. Okay, equals to BQV. I can strike off the V's. Yeah, realize, yeah, strike off the V's here, right? Then what I get is that I get omega. Omega equals to BQ over M. Okay, then this is 2 pi over T equals to BQ over M. So that means my T is 2 pi M over BQX, subscript X. Right? Okay, once I have this, then you can look at the next part. Next part, they say, oh, tau particle is an elementary particle that's the same charge as electron, but there's a mass that's 3 times the electron. It has a mean lifetime of 2.9 times 10 negative 13. Suggest a reason if particle X would be a tau particle, if B is equal to 1.0 Tesla. Okay, so this one, you can calculate this one here. So let's submit the values. Even though 1 mark, right? Okay, if you don't calculate, you just explain in words. I think it's more possible. But I'm going to do the calculation here. Okay, so I'm going to find the period for the tau to do one complete. Remember, this guy, right? When he goes in, he needs to do this spiral. So he must basically go through 1 period, 2 period, and so on and so forth. Definitely timing is more than 1 period. Okay, so we're going to calculate this one over here. Okay, so T tau will be, we're using our formula on top, right? So 2 pi, mass is 3000 times electron. So this is 3000 times 9.11 times 10 negative 31. Okay, then divide by B. B is 1 Tesla. Then Q is same as electron. So 1.6 times 10 negative 19. Yeah, we're gonna work out this one over here using my calculator. Okay, so yeah, 2 times I times 3000 times 9.11 exponential negative 31 divide by 1 divide by 1.6 exponential negative 19. Okay, so I get 0.000107. Okay, this is how many? This is divide by 1e negative 6, right? So this is 1.07 times 10 to the 7. Okay. So 1.07 times 10 power negative 7 seconds to do one period. Okay? But the lifetime of tau is 10 power negative 13. So it cannot be tau because tau will not exist so long to do this orbit. Because the time taken to do one complete orbit is 1 times 10 negative 7 seconds. But tau will disappear in 2.9 times 10 power negative 13. So this guy cannot be tau. Okay? Can. Mental break pause. Any questions you can type in the chat. Okay, and okay, 5A. 5A we have okay, this is more of an application question. So 5A we have this thing is called ground fault interrupter lah. You don't really have okay, we never teach it, but I think the circuit is such that it's easy for you to figure out. Okay, so ground fault interrupter is supposed to be used for places where you have risk of high electric shock lah. So you're sensing coil wound around iron ring that surrounds the wire that transmit electricity to appliance. Okay, so when the device functions normally, the net flux, the net magnetic field is zero. Okay, so however when current flows through a person to the ground below instead of flowing through the return wiring, activates a circuit breaker. Okay, say purpose of iron. Iron is just to concentrate the field lines. Okay, strengthen the magnetic field. Okay, so this makes it uh you will increase your B there lor. So increase your B, then it's easier for you to detect any. Remember your induced EMF, right? Your induced EMF is equals to rate of change of flux over time, right? This is MBA over delta MBA over delta T lah. So you're increasing B. Okay. Use radius now to explain why the circuit breaker is triggered when a fault in the appliance causes a user to be electrocuted. Okay, so let's just look at this setup here first. This setup here, right? At the basic level, if nothing goes wrong, right? This is a series circuit. It goes like that, comes back, and goes out like that. Okay, so there's no alternative path for the current to go. That means whatever current you have coming into here, this I, right, is the same as, hey, I should use another color one. Okay, so basically, use red color for this. Okay, okay, I in, and then I out, right? Okay, I in is equals to I out. Okay, so we have that, right? The flux that is caused by, okay, sorry, the field strength that is caused by the incoming current. Okay, so this incoming current, right, will basically create a magnetic field around it, right? So this incoming current's magnetic field is equals to the outgoing current's magnetic field, just as this is in the opposite direction. So if you're in the opposite direction, right, the fields created by these two guys, right, will cancel out. Okay, but if you have another path, okay, so I'm going to draw this poor dude here who's going to get electrocuted. So this poor dude here, he's over here, like that. Okay, the current, some of the current, let's say this current coming in, this is I1 coming in. Some of the current, right, will go to here. This is I2. Okay, but then some of the current will go to here, I3. Okay, because now this current will flow in to him and then go out from the ground. It goes to the ground there here. So you have some current. Okay, so current comes from this in, comes to here, right? Once it comes to here, it branches out. Some of it goes to him and then to the ground like that. So this portion of current is not returned to the circuit. So there is some current that's going back here now. Okay. But now the important thing is that this incoming current is no longer equal to this outgoing current. Okay. Because some of it is shunted off through this guy and down to the ground. So when that happens, right, what you have here is that this current and this current are not the same anymore. If it's not the same, right, the resultant B field will not cancel off. The resultant B field is not zero. Once a resultant B field is not zero, right, you will trip this sensing coil. You will be able to detect there's a magnetic field in this region of space here, right? Then it will break the circuit. Okay, so this one is a quite interesting setup, but the whole idea is that you need to understand that when you have when you are being you won't be able to you won't be able to try for yourself, but when something is being some poor dude is being electrocuted here, right? Some of the current is going up through him to the ground. Okay, it is okay when, let's say for example, let's say you say that's why people uh to prevent electrocution, right? People work in such areas, they wear shoes that have thick rubber sole. Because when that happens, right, your current cannot flow down to ground. If you cannot flow to ground, there's no path, right? Then there's no chance that you will get electrocuted, because then, yeah, because the shoe is blocking it, Okay, so but now let's say because this is used as shower, right? Shower, all the purposes, obviously, not wearing shoes, this will go straight down to him. Okay, okay. Okay, step one suggests one way to increase the sensitivity of the sensing coil. Increase the number of turns of the coil, That's the easiest way. Okay. Is there any other alternatives that you provided? Let me check. Okay. So increase number of turns on your stop. Okay. Moving on. Okay, this one is quite interesting. This one here you have a loop inside a wire. Wire A. Okay, the wire current goes like this. One round come back. Okay, A to B. Then your loop has a diameter of 2 cm, and then this is a B field of 225 microtesla. Okay, determine the average. Okay, so here the change, right? The change is area. Area drops to 0. Okay, the B field never change. Okay, so work out average. So this induced EMF by Faraday's law. Okay, so we say that E equals to delta MB uh, delta NBA over delta T. So N and B no change. So just delta A over delta T. So sum in the values. So N is 1. Tesla is 25 millitesla. Right? So 25 times 10 negative 3. Area goes from 0. Final area is 0, right? Minus pi 0.01 square. Divided by timing, 50 times 10 negative 3. Yeah, I'm going to just modulo the whole thing. Okay. Then you can get the answer already. Okay, straightforward substitution. All right. So state and explain whether the potential at A is higher or lower than that at B. Okay, so now let's look at this one here right now, right? Okay, so right now your B field is into the wall. Okay, your flux is here. Your flux exists in this space here. They're all into the wall. Okay, so when you reduce the area, right? When you make this guy go into a smaller circle here, right? Just a color for this. Smaller circle. Okay, you are reducing your flux. If you reduce your flux, right? Remember by Lenz's law, right? You will want to or opposite change. So the opposite change, right? Since you reduce the area, because remember our flux will just B times A. If you cut the area, okay, to restore back the flux, right? I can increase my field strength. How to increase field strength? I increase field strength by creating a stronger stronger field into the wall. So to do that, right, my induced current will have to be in this direction. This is induced current. Okay, so because you use a right hand grip rule, you grip the wire this way, the thumb is pointing. If at the position where I mark, okay, the current if your current is going in a clockwise direction, right, the B field will be into the wall, which is what I want. So that means your induced current has to flow from A like that to B. Okay, so there's something weird about this answer key here because they say that induced current will flow from A to B. Hence B is a higher potential than A. Okay, I get what this is. Okay, I understand this. This is in terms of a battery. Okay, okay, I get it. My fault. I confused myself. Okay, so this is like just now we had this question over here. This one. Okay, so this one we need to treat this guy here like a battery. So same thing here. Now this portion is acting like a battery. So if my current inside here goes in this direction, right? If I connect the rest of the circuit like that, right? Then my current go like that. Okay. So B is a higher potential than A. Okay, I get it. Okay. Question so far? Uh,
Mr. Kong, so is it
yeah,
when
yeah.
like there's induced potential, it's always the battery?
When you calculate induced EMF using Faraday's law, right? Your piece of material there, right, acting like a battery. So remember we said that. Remember for prelims we did this question where you have your rod, you have this rod set up, then this guy is rolling across, right?
Mm.
In the B field. So this one, there's no current unless I go and complete unless I go and complete the circuit.
Okay.
So this piece of material, right? If you allow it to complete the circuit, right? This is acting like a battery, lah.
Oh, okay.
Mm, mm, can. But see, the EM questions are very long in terms of the structured questions. I see how much you want to go through. You see time for sure. I'm flexible for timing. You all decide. You all if you all need to all go off together, let me know. Okay, so then we have this okay. So this is oscilloscope. So we hardly do okay, so we don't really do so much of it, but let's see the calculation. It should be okay for this one. Okay, then determine the time-based setting of the oscilloscope if the frequency is 100 Hz, right? So you can see that okay, you should be able to see where where your current repeats itself. So it goes from here, starting here, right? And then it comes to here. Okay. So this is one cycle. One cycle. This is the next cycle. This is the next cycle. Okay. So this one, that means your period is in this portion. Okay. Then you know that T is equals to 1 over F. So 1 over 100, this is 0.01 seconds. 100 seconds lah. 100 seconds. Okay, that's right properly. 0.0100 seconds. Okay, and then we know that. Okay, so you want to find time base. Time base, right? You take 0.0100 divided by extra zero here, I think I did. Divided by 2.0 cm. Because this 2 cm is from here. This one here, 1 cm, 1 cm, so 2 cm. So this becomes 0.005 seconds per cm. So convert to milliseconds, so 5.00 millisecond cm. Okay. Yeah. Okay, determine the root mean square value of the PD. If the Y gain is at 0.5 volts per second, means every vertical, this one here is worth 0.5 volts. Okay, so let's check. So 0 is over here. Let's make the line a little bit clearer. Let's use a fatter line for this guy now. Over here. 0 is here. Okay. Okay. So once we know this, right, then we say, oh, this value here at the top, this is here, I mean, this point here. This point here, right, is one and a half square. So this is 0.75 volts. 0.75 volts. This one here, this is 0.5 volts. Okay. Then you can see for each cycle, right? Each cycle here, you have 1/4 of it. 1/4 of it is at 0.75. Okay. Then 3/4 of it, 3/4 of it is over here at 0.5. Okay, so remember root mean square, we go and we square each value here, then we go and find this area here. Okay, then we square this bottom portion, same thing, find the area here as well. Okay, so this one, this is 1/4 of period, this is 3/4 of period. If you want, you can just write it as 1 time interval and then this is 3 time intervals. But I'm gonna write this differently. So let's see. So to write this, to find VRMS, we square the first one first, so 0.75 square times T over 4, because I take this 0.75 exists for 1/4 period. Okay, then plus 0, okay, negative 0.5 square, and the second portion exists for 3T over 4. Okay, so this is the root mean square, the square part. Okay, the square part. Then we want to find the mean, right? We multiply by T over 4 and 3T over 4 respectively. Whole thing divide by T. Okay, this will give me the mean. Then I square the whole thing. Okay, then once you have this, you can say, oh, I can straight away cancel the T's, right? Okay, then for calculation, right? So I'll take hold on, yeah, I'll take 0.75 square times 1/4. Okay, plus, sorry, without this, okay, plus 0.5 square times 3/4. Okay, then I divide by 1 because bottom we divide TV, now divide by 1, right? Divide by 1. Then I square root the number. Okay, so 0.572. Okay, so this one becomes 0.572 volts. Alright. Okay. Do I need to talk about 6? Anyone needs question 6? I paused for a while, so it was a long question. You need 6 first. You need question 6, just type. Okay. So there is 6, I skip 6. Okay, next one. We come to the question that I changed, right? 9. Okay, so what happened was that I took from some school, I can't remember which school, but I copy pasted the wrong answer key. Then the intelligent me forgot to save which school is which school, right? So I cannot find the same question. Okay, but I found almost the same question. They just changed the numbers. This was 2 JCs in the same year. So two JCs in the same year, they basically use the same same question, right? And then yeah, then they just change the numbers more or less. But then I think this school asks a little bit more stuff. Right. So and I think the first version it was a 6 mark question. Okay, but this other school one managed to change into a full part paper 3 long question. Okay, so we see how much of it can do. We have about one half hour left. I think should be just nice for it, right? Right. Okay, so this question 9, magnetic flux linkage. I'll not define for you when read our own. Remember this one flux linkage need to mention multiply by number of coils. Very important. Okay, flux and flux linkage, the difference is now number of coils. Right. Okay, next we have a solenoid, diameter 6 cm, 540 turns. 6 cm, 540 turns. Placed in uniform B field as shown. Okay, variation of the flux density is shown if you 9.2. So flux density starts from, you can see the variance law. So it goes like that. Okay, calculate maximum magnitude of the induced flux. Okay, maximum magnitude. Okay, so let's write out the equation again. So by Faraday's law, your E by Faraday's law, E equals to delta phi, what the hell, this thing, delta phi over delta T. So if I'm looking for maximum induced EMF, right, I'm looking for the maximum rate of change of flux linkage. Okay, so here, right, there are just two changes. One, okay, the change is all due to your B, right? So it's because of your area and number of coins never change. So here you have two portions. This portion goes from 0 to 250. Okay, this one goes from 250 down to 0. Okay, but the second portion happens in a shorter period of time. If it happens in a shorter period of time, right, for the same change, right, the gradient is actually larger in terms of magnitude. So I'll be using the second one to calculate that, correct? So submit the values. So this is same thing. This is equals to NBA, right? N and A not changing, so the right hand side. So N A delta B over delta T. Okay. So what's N? N is 540. Okay, so 540. Then diameter is 6 here. So times pi 0.06 6 cm, right? 6 cm. So 0.062 square multiply by change in B. Okay, because I only care about the magnitude, right? So I go 250. Okay, okay, so 250 lor. So okay, 250 minus 0 times 10 negative 3. Okay, happening for how long of time? Happens from 6 seconds to 7.2. So this is 7.2 minus 6.0. Okay, then go and solve it lor. Okay, so this one should be straightforward lah. Don't have to figure how to do it, right? Can? Okay, next we have a thin copper sheet, the supporter and rigid rod that hangs between the poles of magnet. Sheet X is displayed to one side and then released when it oscillates. So basically the oscillation happens along this plane. So, like that. So it starts from here, it goes to center, it comes to this way. So it's going left, right, left, right, left, right, this way. Okay. Then a motion sensor is used to record the displacement of X. Second thin copper sheet is replaced. So this guy is like that. Okay. So you can see, let's just draw the first sheet over here. First sheet is over here like this. This is X. Okay. So now I use the motion sensor to record this pattern. Okay. Now you are plotting the graph. You see that there are two graphs here. All right. So then you have one that goes this way. The other one that goes a little bit smaller and smaller and smaller and smaller. Okay. So this process, I think you should know it as damping. Okay. Deduce which copper sheet is represented by the dashed line. All right. So let's go back and look at the sheets again. Okay, remember if you want to remember your copper is going through the B field created by the poles of the magnet. So as it goes through, right, it is going from an area, let's say over here, there's no flux. comes into center, there's an increase in flux. So increase in flux means that by Faraday's law and Lenz's, right, there will be induced EMF and therefore induced current to oppose a change in flux. Okay, so remember the systems don't like change. Okay, so you go from here to here, you try to oppose a change. But once it's inside, again, once it's inside here, right, you swing outwards, right? Again, you go from, let's say, from A to B, right? A has higher flux linkage than B. So again, this is a change that the system want to resist. So again, you oppose it by creating the flux in the opposite, the EMF in the opposite direction now to oppose the change. Okay, so with that happening, then let's look at the two sheets now. Which sheet is more conducive for creation of for current to flow? You can see that for sheet X, it's basically there's no impedance at all. There's no gap. So current can flow like okay, I don't know the direction, but basically it can flow in circles like this easily. Okay, even if you want to flow in the big path, let's say like that, right? You want to flow a big path like that, it's also possible. Easily, right? But this guy here, right, you can see because of the gaps here, right? You cannot have current that goes like this really. Okay? You cannot have current that goes like because now there's a gap. We did this a lot when we have remember the jumping aluminum ring one, where we cut a gap in the ring. Remember we had this experiment where you have this setup here, and then this is basically like a magnet, right? Then you put a ring here, right? Then the ring is a complete ring. Yeah. If it's a complete ring, right? Like that, right? Complete right there, right? You will jump very high. But then if you introduce a gap, let's say this ring has a gap. Let's say how to draw a gap ring, I try. Like this. Like that, right? It won't jump because there's no complete loop for the current for the induced current to go through. For induced current to flow. So there's no induced current at all. Okay. So in this case here, right, this copper sheet wire, right, will not be able to induce much current because of all the gaps in the middle. So these gaps make it hard for any induced current to flow. So you don't have induced current, right? You don't have an induced magnetic field to oppose the change. So again, the damping will be lower. Okay, so that means this, label this guy, this is X and this has to be Y. Okay, so explanation, let me look at what the other school has written and then we go from there, okay? Wow, what the hell? What is it? Yeah. Okay. So it's good if you can write the word eddy currents, if not, it's okay. All right. Okay. Anything you want to clarify about this one here? Oh, light damping. Okay. Okay. Yeah. I move on. Okay, next part is the one that I haven't done yet. Oh, you ACS, right? AC together. Okay. I haven't done this yet, so first time looking at it. So okay. So usually I will look at it the night before but this one because I put it in like late last night, so I didn't have a chance to look at it. Okay, so we have a PD of V320 sine 100 pi T. So this one we can write the standard formula as well. So just as some comparison. So V equals to V naught sine omega T. That means I know over here, even before I do anything, right? Therefore, my V naught is equals to 320 volts. My omega is equals to 100 pi. Okay, so these are what I can establish. Okay, then I just set up this circuit. This is 120 ohms, and then I have a diode. Okay, this diode, obviously, diode only allows current to go in a single direction. In this case, the direction will be this direction. Okay, so if you can connect it to AC, right, it will allow, remember AC will flip regularly. So current going this way, no issue. Current want to go opposite direction like that, cannot because this guy has infinite resistance when it is in reverse bias. Okay, sketch on figure 9.7 from t equals 0 to t equals to 40 milliseconds. Variation with time t of PD across source, PD across R, and then PD across the diode. Okay, so let's see now. Okay, so we are given all this graph to draw. Okay, let's try. Okay, first thing you know, because they give us timing, right? So we need to work out what is the period first, because that will tell us how many cycles we need to draw. This one cannot just anyhow whack, because this one is scaled. Everything, the numbers are given there, so you have to draw to scale. You cannot just whack like 3 cycles or what. Okay, so for this, let's work out the period lah. So we know that uh we have already established, and just write here lah. So we know that omega, irritating me. Omega is equals to 100 pi. So period is equals to 2 pi over omega. So this is 2 pi over 100 pi. So this is 0.02 seconds. Okay, so 0.02 seconds. So 40 milliseconds is basically, okay, so that means so 40 milliseconds is equal to 0.04 seconds, which is equal to 2 times our period. 2 times our period. 2 times our period. So that means draw 2 complete cycle. Okay, then we know maximum voltage is 320. Okay, so first thing to draw. Okay, a PD across a source. Okay, this is all PD. So PD across the source quite straightforward lah. Okay, so we go to start, because this is a sine curve, right? So sine curve start from 0. Okay, positive sine curve. So 0, 320 is here, over here, back to here, then back to here, and back to here. So draw 2 complete cycles. Let's go do a quick sketch. 1, and it's damn ugly. So 1, try. I think crap lah. My accuracy not very nice. One more time. 1. So drawing beats, I think is easier. 2, 3. As accurate as you can, please. 4, something like that. Okay, PD across source. Okay, PD across R. Okay, this one is a bit more interesting. Go back this diagram here. Okay, so we're going to treat, okay, they never tell us, but we're going to treat one side as positive. This side is positive, this side is negative. Right. When this, okay, so when your current is in forward bias, when that is forward bias, right? Your current goes this way. It goes like that. So in this direction, right? Your diode is 0 resistance. Okay. Then this guy has high resistance. So you want to find out, you want to find VR, right? VR, right, is basically is resistance of R over resistance of R plus resistance of diode times EMF. Okay, so if you're in forward bias, okay, forward bias means your RD is effectively 0. So your VR is just R over R plus 0 times EMF, so equals to EMF. Okay, then if you're in reverse bias, right, your RD tends to infinity. Infinity. So your VR, your your VR is equals to R over R plus infinity times E, whole thing is equal to 0. Okay, so when it's in forward bias, your VR, right, is equals to your EMF. Okay, so your curve will look like this now. Okay, so let's take the positive portion as forward bias. So when you're in forward bias, no issue. Forward bias, right, the curve is the same. Like that. Like that. So these 2 portions are the same, right? So damn it. I think this is like when the iPad starts to It's good to erase it once though. Yeah, it's good to clean up, to reset once in a while. Okay, like this. Okay, then this one I'll draw a second portion again as well. Like this, right? Okay, when it's in reverse bias, reverse bias, right? The diode is at high resistance. That means it will take up all the potential difference here. VR will be zero. When it happens here, that means we expect your curve here to become zero. I'm gonna use a slightly fatter line for this. Fatter line for this. Okay, I'm gonna check my answer at this stage first. Make sure that we are on the right track for this one. Alright. Okay, what's my what happened again? They never even draw. Line at zero for yeah, okay. Okay. Next one. Then we're going to draw PD across diode, right? PD across diode will be opposite of this guy, lor. Okay, so this one will be like that. We're going to draw it out. One stretch. 0, 0. And PD is should be negative. Negative, right? Like that. Okay, this. Trying to draw it as nice as possible. I'm not really checking it now. Let's see, make sure everything's right. Negative x only. Yeah, so okay, so yeah, 9D1 is positive sign. Okay, so if 9D1 is positive sign, that's positive for first half of cycle. Then if goes on, negative 0 for first half of cycle, negative V for second half of cycle. Right? Okay. I'm glad I changed the question to include this because this one is a good one. Okay? And then you choose. I think almost there, right? Just left some more calculations. Okay, average power dissipated. Average power dissipated in resistor R. Because now, okay, so this one, if it's a normal circuit without diode, right? Without diode, this is just, okay, so the normal circuit is like that, right? This is a normal circuit, like this. This is normal. Okay, so for this guy here, right, the average power is just VRMS square divided by R, right? Okay, so this one we can just do, we know that this is square root of V naught over square root 2 square over R. Okay, so in this case, this will become 320 over square root 2 divided by 2 R power. Then divide by, did they tell me R value? They give me R value. 120 ohms. Okay, 120 ohms. 120. 120. Okay, but because now I have diode, right? I have diode now, right? Okay, so I can't. So I only get half of the cycle. So you half the value some more. So you half. So this one will become your P is equals to half of VRMS square over R. Okay, so this whole thing becomes half 320 over square root 2 square divided by 120. Yeah. Yeah. Okay, so make sure this half them. Okay, anything else? Almost done. Define RMS, I leave it to you. Determine RMS current in the resistor R. So this one, just do, okay. So you can go from V naught, okay. You know that IRMS is equal to just VRMS over square root 2. This one, uh, huh, 2R. yeah, this one to be very careful because okay, we half the cycle. Okay, because we have the diode there. So this one is over V2, right? So this one by right should be V naught over square root 2. Then divided by R. So you have the R divided by R. But because we have half cycle only, right? So this one becomes V naught over 2. Okay. If you can't get from here, right, what you can do is that this method is not so sweet here. You use your average power. So average power on top. This first one, the calculation should be all correct. Well, let's take the value lah. The value is what is this? 213. Even finish the working. Okay, never mind. 213 watts. Okay, 213 watts. Okay, so I want to find. Okay, there is no average power, right? It's just equals to IRMS square times R. So this is 213 equals to IRMS square times 120. So IRMS is equals to 213 divided by 120 square root. Okay, so 1.332, 1.33. Okay, 1.33 ampere. Okay, so I'm going to show the wrong method as well. The wrong method here is to just take, okay, if you wrong, if never factor, never factor diode effect, diode effect. Okay, so what you have done is that you will just take IRMS equals to I naught over square root 2 equals to V naught over R square root 2. Then you will have, what's V naught? 320, right? 320 over 120 over square root 2. Then this one, how much you get? 320 divided by 120 divided by square root 2. I get 1.88, 0.89 ampere. Okay, but it's not. So this is a wrong method. Okay, okay. I think that's the last one. Okay, 20 marks done. Okay, so we will take Friday to do nuclear. Okay, so Friday should be the same time. I might start a bit earlier because I consult at 11:15, so I'll start a little bit earlier probably. I'll let you know again. Okay, if you have any questions, you can stay on. Otherwise, we are done. Can go off. Thank you.
Bye bye.
Bye. Bye.